Okay, guys, these are your notes over light and color. So, for the longest time, there was this debate. Is light a particle or a wave? It went on for literally hundreds, if not thousands of years. Uh, Basically, people thought that it might be a wave, it might be a particle. And so there were some big ideas behind both of them. So let's start with light by talking about those two big ideas. So the first one was proposed by Isaac Newton, and Isaac Newton thought that light was a particle. He proposed that it was a corpuscle, uh, and he said that it was a corpuscle because basically reflection and refraction could be explained with particles. For example, if you throw a tennis ball off the wall, it's going to bounce off and come back to you. In the same way that if you throw light at a mirror, it's going to bounce off and come back to you. If you throw a tennis ball into water, it's going to change its speed, it's going to bend, it's going to change the direction it's moving. Same way, if you throw light into water, it's going to change its speed, it's going to bend. So Newton thought that light could be a particle. Uh, for the wave argument with light, there was about a couple hundred years passed, and there were several different things that came along. So one of them was Poisson's spot. It was kind of it was the it was the thing that kind of started the motion to showing light was a wave. Basically, it proved that light could diffract. And if you take your fingers and you hold them up to your eye, and you kind of like hold them not very far apart, but like just far enough apart where you can still see light through them. There's a little blurriness around the edges, and that's not necessarily because your eyes aren't able to focus. That's because light is diffracting around your fingers. And so that kind of shows that light is diffraction. Now, what this spot is you take a laser beam and you shine it at a little ball, and whenever the light hits that ball, it gets bent around the ball, so that whenever it comes to the back, it basically has a shadow. So some of it goes out like this, and some of it forms a little shadow. There's a shadow right here and right here, but there's a point of light that forms right here. So if we imagine this green laser coming in towards this ball right here, so if we have a green laser coming in toward that ball, some of the laser gets bent around this way and it goes out like that, and some of it gets bent around this way and goes like that, but a little bit of it bends around the barrier and forms a point at the back. And so that was what Poisson discovered. Young's double slit experiment was basically proving that light had both constructive and destructive interference. So basically what Young's double slit experiment did was it proved that light both constructively and destructively destructively interfered with itself. And you can see this in these light and dark bands. So this is area of constructive interference. So constructive interference occurs here, and destructive interference occurs in these gaps. All right, that's where the light's canceling itself out. All right, so still had this debate raging. Basically, at the end of the 1900s, at the end of the 1800s, everybody thought that light was a wave. We thought it was all settled. But then a man named Planck, his first name was Max, in case you want to know, Max Planck observed the black-body curve discrepancy. And so essentially, we don't need to get into this too much, but basically, if you were looking at classical theory, the hotter you got an object, the more energy it would emit, and if you got it to a certain temperature, it would emit an infinite amount of energy. Obviously, couldn't happen. So basically, he fixed it. Planck fixed this problem by fudging the numbers a little bit and saying that light came in little packets of energy called quanta. All right. So Max Planck came up with this idea of quanta, and basically what he was doing was he was solving this black body problem. Quanta are these tiny amounts of energy. All right. So basically, the final person who solved all of our problems, as so often happened in physics, was Einstein. And he solved the problem. He said light is both a particle and a wave. It comes in small but discrete independent amounts called quantum. And photons are emitted when excited by Okay, so basically what happens is whenever you have an atom and you've got these electrons, if you remember from chemistry, they had different energy levels they could have. So like these are the different energy levels of the electron. And if it jumps from one energy level to the other, if it jumps down an energy level, so if it goes down, it emits a photon. And it only emits one photon, which represents one like single wave of light. And so what we visualize as light is a series of these photons. Now, light is so pervasive, there's so many of these that we don't really perceive it as having an end, but it does. It's just that they're very, very, very tiny. So photons are emitted when electrons jump back down energy levels, but this only happens in very particular ways, which is why you only have very particular colors that you can see sometimes. Okay, next up, the electromagnetic spectrum, the electromagnetic waves. So basically we have all these different waves. The important thing that you need to know is that if you move from one side to the other, the energy increases. So when we go from one side of this to the other, the energy is increasing as you move from radio waves to gamma rays. So radio waves have the least energy, and gamma rays have the most energy. That's the reason they can make a Hulk. All right? On the other hand, the radio waves also have the least frequency. They have the smallest frequency, and I guess we should let's say that smallest frequency. So the radio waves have the smallest frequency, and gamma rays have the biggest frequency. Now, if you remember from waves, you got V is equal to lambda F, and so if we bring the frequency up, the wavelength has to go down. And so radio waves have big wavelengths, and gamma rays have small wavelengths. And remember, this symbol is a lambda. It's the symbol for a wavelength. All right, so as we move across, we're getting higher and higher energy levels. The energy level for light, you don't necessarily have to know this formula, but it's equal to HF. H is a very, very tiny number, but the energy is connected to the frequency. So the higher the frequency, the more energy it has in light. So radio waves, obviously, we use for communication, as do we use microwaves. So microwaves and radio waves are both used for communication. Typically, radio waves are used in your car to get to your car. Microwaves are typically used for cell phone communication, actually, in addition to obviously heating up your food. Infrared is what carries heat, and some animals like snakes can see in infrared. We, of course, see in the visible spectrum, but notice that we have only this little tiny spectrum right here that we're able to really see. Everything else is kind of invisible to us, even though it's all technically light. Ultraviolet, some animals have the ability to see in this, such as bees. So bees and some birds. X-rays, you're getting into the more dangerous area of the spectrum. Ultraviolet is more dangerous. It's got more energy. That's the reason it's a little bit more. That's the reason that's the thing that you have to protect yourself from the sun for. X-rays are a little bit more dangerous. That's the reason the people get behind the barrier whenever they take an X-ray of you. It's also the reason the X-rays can pass straight through you rather than like visible light. None of us are transparent to visible light. And gamma rays are the most powerful. Okay, so real quick, two definitions real fast. Transparent, it means to be like clear to the wave of light. So things can be transparent to different things. So for instance, like glass is transparent to visible light, but it is opaque to ultraviolet light, and opaque means to not be able to have the light pass through it. So some things are transparent and other things are opaque. Transparent, again, light can pass through. Opaque means it can't pass through. Microwaves, for example, if you look at the little grid pattern on the microwaves, that grid pattern is opaque to microwaves, even though visible light can pass through it. So remember, for visible light, you've got Roy G. Biv as a way to remember the colors that you go through. And the same thing applies to Roy G. Biv. That's red, orange, yellow, green, blue, indigo, and violet. Same thing applies to this as did the spectrum as a whole. As we go across, we are increasing the frequency and the energy, and as we go across, we are decreasing the wavelength. Okay? So that's a brief rundown of the electromagnetic spectrum. Each of these has a different thing you can do with it again. So radio waves, communications, heat is infrared, visible light is what we used to see. Ultraviolet light, some animals used to see with it. It's kind of interesting to look at. If you go Google online, ultraviolet flowers. In fact, I'll just show you one real quick. Okay, I found you an example of the flowers. It's kind of cool. Here, this is an example of a flower that has been taken in both ultraviolet and visible light. So on the left is the ultraviolet, and then this is the visible. And what you should notice immediately is that the ultraviolet has a lot more distinction than the visible, and the visible light just looks yellow. But since bees can see in the ultraviolet, the flower developed a way to basically guide the bee into where the pollen was, because that's what it wants it to do. So that's pretty cool, right? Different animals can see in different frequencies. By the way, this is not exactly what the bee sees. We don't know quite what the bee sees because perception is in your brain, but that's just a representation of the different frequencies of ultraviolet light that would be produced. Okay, finally, how do we see? So basically, in your eyes, you have a couple of things that help you see, and those two things are rods and cones. So rods and cones are two of the things that allow us to see. The rods are how you perceive brightness. So if you're in a dark room and you notice that there's shadows, or you notice that there are areas of brightness, that's your rods helping you to see. However, if you are if you're trying to see color, if you can see color, then those are your cones. And your cones are what allow you to see color. So I've got a couple of videos that show you this over the course of the week. It's kind of interesting to think about. And there's a video on color blindness. So if you can't see color, there's a little video to help you understand why that is. All right. For color in physics, we're going to have two things. So the two things are going to be color addition and color subtraction. Okay, those are the two things that we will be dealing with. And for each one, you have different colors that form the primary colors. Now, normally I would get to demonstrate this with a ray gun, so you're going to have to bear with me a little bit here and just maybe trust me a little bit. But I've got a picture I can show you to help this out. Okay, so now I'm going to add, let me just show you this picture real quick. So this is color addition. And we're going to have to look at this in a little bit more depth. But they usually have this really cool demonstration I can do with this, but unfortunately, since we're all at home, I can't. But so that's what the demo with ray guns means. But basically, this is how color addition works. You have your primary colors here. So these are your primary colors, and you have your secondary colors here. These are your secondary colors. And basically, by combining these in different amounts and ratios, you can create all the colors that exist in the world. So for example, if we combine red and green together, we get yellow. If we combine green and blue together, we get cyan. And if we combine red and blue together, we get magenta. So if you're having trouble kind of visualizing this, look at the little sheet here, or the little color wheel here. We've got red, green, blue on the outside, and then as they mix, we get the different colors combining. So red and green create yellow. Blue and red create magenta. Green and blue create cyan. And the all three combined create white light. And so we get that. So the other thing is a complementary color, or complementary color. A complementary color is one that adds together to make white. So it adds to make white. Okay? So color addition happens in TVs, projectors, and that was terrible. Let me rewrite that. Projectors and like cell phones. These are things that that is adding light. And the thing you got to ask yourself is, does it like glow on its own? If it's glowing on its own, it is emitting light, and if it's emitting light, it's performing color addition. Okay, so let's go through how these work. What do you mean when you add these together? So, for example, red and green. If I add red and green, I get yellow. If I add green and blue, I get cyan. If I add red and blue, I get magenta. If I add red, green, and blue, I get white. But what if I add green and magenta? Well, green is green, but magenta is red and blue. So I'm really adding red, green, and blue together, which means I get white. Blue and yellow, I'm adding blue, but then I'm also adding red and green, so I'm getting white. Red and cyan, cyan is technically green and blue, so I'm adding all three together again, so I get white. All right? And then finally, we've got color subtraction. So color subtraction is anything using pigments or reflecting light. And so basically by combining these pigments in different arrangements, you can create all the colors of the rainbow as well. But this occurs when things are reflecting light back to you. So you basically have two ways to perceive light. One is the object can emit light, and again, that's something that glows on its own. If you can see it in a dark room, like if you turn all the lights out in your room and you can still see it, that means it's emitting light. If you turn all the lights out and you can't see it, it means it's color subtraction. And so if it's color addition, you'd use the primary colors as red, green, and blue. If you're doing color subtraction, CMYK are your primary colors. Cyan, magenta, and yellow. And then K stands for black. K stands for black. All right? So the primary colors for color subtraction are CMYK. And if you add cyan and yellow, you get green. If you add cyan and magenta, you get blue. If you add magenta and yellow, you get red. All right, so it's a little bit different. And then you can basically use the K to darken it up. So let's say you want forest green. Well, then you do cyan, yellow, and you throw in a little black. All right? If you want navy blue, you do cyan, magenta, and you throw in a little black. All right? So color subtraction removes, basically each pigment removes a color. So cyan removes the color red. Magenta removes the color green. And yellow removes the color blue. So when you're doing color subtraction, you're adding pigments together, what you do is you start off with like red, green, and blue, and then you look and see which colors you remove. So if I do cyan and magenta, cyan removes red, so red is out. Magenta removes green, so green is out. So if I add cyan and magenta, I get blue. So cyan and yellow, again, start with red, green, and blue. Cyan removes red, cross out red. Yellow removes the color blue, cross out blue, and you're left with the color green. And you can do these in all kinds of different combinations. For example, if I did magenta plus yellow, what would I get? I would get red, green, and blue. Red, green, and blue. Magenta takes out the green. Yellow takes out the blue. So I'm left with red. Okay, guys, so that finishes up the notes. Next week, I'm going to have a little thing to start the week showing you how the color addition and color subtraction kind of interact with one another, in addition to going through the rest of the topics with light and color. All right, so I hope you have a wonderful week, and I hope to see you all soon.